Welcome back, everyone. So I have a new video lesson for you, and this time we're starting a new idea. The new idea we're starting is the idea of building new functions from old ones. The core of this idea is that we start with functions that we know something about, often a lot about, and then we build a new function off of that. And it turns out that we can use a lot of what we know about the old function to inform our understanding of the new one. So the ways in which we're going to build new functions from old ones are going to be transformations of functions, which is what we'll be doing this week and also some of next week, and then compositions and inverses, which are both going to happen next week. So for transformations, as you can see, the word is plural. There's more than one kind of transformation. So we're going to break it up into a few parts. So this lesson is going to cover part 1 of transformations, which are going to be translations. So a lot of what we do with transformations is going to be graph-based. Not everything, but almost everything. So you'll notice that I've already started here with the graph of the function f of x equals x squared. Should be real familiar. We worked with it before. I just want to label a few things on it, okay? So this point here at the bottom of the graph, that's the vertex. Notice that it happens at the origin. And then I'm going to zoom in so that you can see my writing really, really clearly. I also want to talk about the domain of this function. The domain is not terribly exciting. The domain is just all real numbers, right? We'll make sure to look at an example later where the domain isn't just all reals. And the range of this function is the non-negative reals. So it starts at 0 and then goes to infinity. Now what I'm going to do is I'm going to introduce a new function. I'm going to write it underneath here. G of x is equal to x squared plus 2. So let's see. The way that we're going to do this is we're going to draw the graph, and we're not going to do this every single time, but you'll notice we do it a bunch. So we're going to build a little table. In the leftmost column, we're going to put the value of x. Then here we'll figure out the value of x squared plus 2. In other words, we're figuring out the value of g of x. And then just to kind of keep ourselves honest, we'll make sure to write the point that we're talking about here that we're then going to plot on our graph. Excuse me. You can pick any values of x that you like. So maybe we can do a couple negative ones, a couple 0, and a couple positive ones. All right, so let's see what we have. So if x is -2, we have -2 squared plus 2, which is 4 plus 2, which is 6. So the point there is the point -2, 6. If x is -1, we have -1 squared plus 2, which is 1 plus 2, that's 3. So -1, 3. 0 squared plus 2, that's just 2. So we have 0, 2. 1 squared plus 2, that's back to 3. And 2 squared plus 2, that's back to 6. So here we have a few points in blue, so let's go ahead and plot them. So -2, 6 is there. -1, 3 is there. 0, 2 is here. 1, 3 is here. And 2, 6 is here. So we haven't sketched in the graph, but I'm hoping that you can already tell that what we've got going on here is exactly the same shape, but higher. I'm not going to write this right now. We're going to do an example in a minute where we will write it. But we can say that it looks like the blue graph is identical to the red graph, just shifted up 2 units. All right, so let's play with this a little bit more, and I want you to notice a couple of things. I'm not going to spend a lot of time here because we'll spend more time in a minute, but if I take any point on the blue graph, like for example our friend 2, 6 here, okay, and then I sort of dot down, I can find a point directly underneath that one that has the same x-coordinate, but the y-coordinate is smaller by 2. If I start over here, so this is our friend 1, 3. If I dot down, there is a point on the red graph, same x-coordinate, but the y-coordinate is smaller by 2. Now check it out. If I have here any old point, so I'm specifically not picking a nice one, I'm just picking some point on the blue graph. Let's call its x-coordinate x and its y-coordinate consequently is g of x, right? Because every point on the graph of a function is an input-output pair. If I dot down to the red graph, there is the point. So again, they have the same x-coordinate. And because we're now on the red graph, which is the graph of f of x, its y-coordinate is f of x. But as we've noticed for the other two examples that we just did, and I'm going to write this here, we see that g of x is too bigger than f of x. So if you put an input into the function g, and you put that same input into the function f, you will always get an output that's bigger by 2 out of g than out of f, okay? So I'm going to write here this transformation only impacts outputs or y-coordinates if we're talking about a graph. So you'll sometimes hear me refer to this as a y-coordinate transformation. So notice that over here, remember, we were talking about, so this was for f of x. We talked about the domain and the range of f of x. Well, let's do the same thing for g of x. So we have both graphs. Let's see what we can see. And what we see is not surprising. Because our transformation only affected the outputs, only affected the y-coordinates, there's no change to the domain. The domain was all reals. It still is all reals, right? So I'm going to put here not changed. But the range, right? So if we go back to the graph here, what do we see? Well, the original graph, the red one, the lowest point on it was the origin, the vertex, 0, 0. So the smallest y-coordinate of any point on the graph was 0. If you look at the blue graph, there's the vertex. It's the point 0, 2. In fact, let's write that here. Our graph is getting a little bit claustrophobic, but that's okay. So the smallest y-coordinate of any point on the graph of the blue function is 2. So the range there isn't from 0 to infinity, it's now from 2 to infinity. So we'll put here range shifted up. By 2 units. All right, so let's go to the next page, and I want to continue this. You'll notice I already have f of x equals x squared waiting for us. There it is. And we are once again going to graph another function, but this time we're going to look at g of x equals x squared minus 3. So unlike the first example, I'm actually going to ask you a little think about question, kind of, what do you think the graph of g is going to look like? So again, this is one of those things that some of you might be like, oh, well, obviously, da-da-da-da-da-da, and others of you might be like, I don't know yet, I don't think I get it, and that's fine. But after we actually do the graph of g, we'll go back and we'll answer this question, okay? And then much the same way, I just want to have it here. I want to be talking about domain and range. So the domain of this function that we're starting with is all reals. Oops. The range starts at 0, goes to infinity. And then once we're done over here, we'll also look at the domain and the range of g. So again, kind of as part of that think about piece, you could be thinking about what do you think is going to happen. Okay, so we are going to do the chart. Again, you'll notice you won't have to. In fact, in later examples, I'll give you a workaround that makes it so you don't need the chart. But it's handy at the beginning to know that this is an absolute fail-safe. It's always here for you. Okay, so again, much like before, since the domain is all real numbers, I'm just going to pick a few values. So let's do -2. Let's do -1. Let's do 0, 1, and 2. Okay. To extend this a little bit. There we go. All right, so -2 squared is 4, minus 3 is 1, so the point is -2, 1. -1 squared is 1, minus 3 is -2, so the point here is -1, -2. 0 minus 3 is -3, so the point there is 0, -3. And here we have 1 minus 3 is -2. So we have 1, -2. And 2 squared is 4. Minus 3 is 1. So we're back to 1. All right, let's plot these points. And I'm already seeing a problem with our graph, but that's okay. We'll make it work. Okay, so let's kind of scroll here so we have it. So -2, 1 is there. -1, -2 is there. 0, -3, so I'm going to extend that down. So, not very good planning on my part, but that's okay. We will make it work. Alright, and I'm just going to label -3 as being down here. So there is 0, -3. Here's 1, -2, and back to 1. So what I'm hoping you see here is that, again, with the blue points, we're flushing out the exact same shape that we had with the red, but shifted down this time. So once again, I'm sort of sketching this in. This is not perfect. It doesn't need to be perfect, just needs to be sort of the right idea. As we know, graphs are rarely perfect. They're not there for precision, they're there for general ideas. All right, so there is the blue graph. So this is the graph of g of x equals x squared minus 3. And so let's go back to our think about question over here where it says, what do you think the graph of g of x is going to look like? So I'm going to write here, just like the graph of f, just shifted down 3 units. So again, I want to very quickly do this with you. I'm not going to do a lot of examples, but what we're seeing here is that every single point on the graph of G, so this one is 1, -2, it has a point directly above it on the graph of F, right? So this point has the same x coordinate, but the y coordinate is 3 bigger. And by that same token, if I pick some random point on the graph of G, so let's call this x comma G of x, and then I dot up, boop, 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 da-da, ba-da, there's my point on the graph of F. It has the same x coordinate. So on the one hand, this point is x f of x. But on the other hand, what we're seeing is we see that g of x is equal to f of x minus 3. So if we just subtract 3 from the output that f produces for the input x, we get the output that g produces for the input x. All right, let's really quickly talk about domain and range. So again, this transformation only affects outputs. It only affects y coordinates. So not surprisingly, the domain is the same as it was. Well, what about the range though? Again, the vertex of the original function, which is this point here, the lowest point, is the origin. Well, the vertex of the new function is down here. So what we're seeing is the lowest output that the blue graph ever shows us is -3. So notice that the range is now from -3 to infinity. So notice that it's shifted down 3 units. Okay, so let's make a summary and then we'll end this lesson. So summary, the graph, in fact, let me not say it this way, let me say it this way. Adding or subtracting a value, let's call it C, to the output, so the new function is the original function plus some value C, results in a vertical translation. And the word translation means the same thing as shift. If C is positive, in other words, if we're adding, the shift is up. If C is negative, the shift is down. So this concludes our conversation about what are called vertical translations. So we did an example where we shifted up. That's here. And then we did an example where we shifted down. That's there. And then we summarized it here. So in our next lesson, we're going to talk about horizontal shifts. So stay tuned for that. See you soon. Bye.